Hi everyone, Mr. King here. We're going to finish up our growth and decay lesson and examples with part 3 here, but before we do, I want to add one last bit to part 2. We had just done a radioactivity problem. We found the decay formula for radioactive neptunium, I believe, and by the time we got to the end of our work with that lesson, we had solved for the rate constant, and we found that it was ln of 2 divided by 65. Now, 65 happens to be the half-life of the radioactive substance. So what this means is the following. If we know the half-life of a radioactive substance, then we can take the natural log of 2 and we simply divide by k, the rate constant, and we've got it. So in this case, we're asked to find the equation of the curve that passes through the point 1, 3, having the slope y over x squared at any point on the curve, coordinates x, y. So this is written slightly differently. And what we have to realize here when we look at this is that when we see the word slope here and we see y over x squared, that's another way of saying that dy over dx is equal to y over x squared. And now we can solve this by separation of variables. And that's going to give us our familiar dy over y when we divide each side by y. And when we bring dx to the other side, we will see that we have 1 over x squared dx on the right side. Again, we can anti-differentiate or integrate like so. And we get natural log, the absolute value of y on the left side. 1 over x squared might look daunting for a moment, but remember, 1 over x squared is x to the negative 2. And if we want an antiderivative of that, we're going to need an x to the negative 1, aren't we? We're going to need a negative x to the negative 1, which is negative 1 over x. And so negative 1 over x is the antiderivative, and then we're going to say plus c1 here. We don't really need that little scratch work on the side anymore, do we? And we'll exponentiate now. That will give us the absolute value of y is e to the c1 e to the negative 1 over x, like so. Now the right side is interesting. If we take a look at it for a moment, we can see that right here e to the c1 is a positive quantity. And e to the negative 1 over x is also a positive quantity. And so when we drop the sticks here, we can simply say y is equal to c times e to the negative 1 over x. And in this case, we've let c take the place of e to the c1, like that. Now we're going to use initial condition for the particular solution point 1, 3. And when we plug this in, y is 3. This will allow us to solve for c. This is e to the negative 1 over 1. And that's e to the negative 1. So we will have 3 is equal to c over e. And from that, we can see, interesting language there, that the letter c, our constant, is 3 times e. And that allows us finally to write our function. It's y is equal to 3e times e to the negative 1 over x. And x is greater than 0 here. Now, why is x greater than 0 here? Well, we go back and look at the initial condition for this particular solution, and it is 1, 3, which is in quadrant 1. Quadrant 1 is above the x-axis. If we go back up to the original differential equation, we can see that x cannot be 0. And remember, the solution to a differential equation cannot pass through a discontinuity in the slope field. And a discontinuity in our slope field would mean we'd have to go through that x-axis. We can't do that. and the initial condition is above, so hence we need to say that x is greater than 0 here. If we were to graph y equals 3e e to the negative 1 over x, it looks like it would never be below the x-axis, let alone on the x-axis. I think you'd agree with me on that. If we take a look at the slope field for our original differential equation, dy dx is equal to y over x squared. That is a curve with a slope of y over x squared. The slope field looks like this, and we can see that the numerical solution that goes through 1, 3 is the red dots, and then the blue solid curve is our solution, our particular solution to this differential equation, 3e times e to the negative 1 over x, which is the actual curve. And as we see here, it does not, the solution that is, does not go through the x-axis. In fact, it never even touches it, although it's hard to see in this view. And that wraps up our solution to that differential equation problem. We're going to wrap up part 3 with Newton's law of cooling, which is a pretty cool application of differential equations and then the resulting temperature functions that we can create for objects. So Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the temperatures of the object and the surrounding environment. So that temperature differential is a key driver of the rate of heat transfer, in fact. So in our example, we're going to let y represent the temperature in degrees Fahrenheit of Mr. Franklin's teacup in a room that he keeps at a constant 60 degrees Fahrenheit. The teacup cools from 100 degrees to 90 degrees in 10 minutes. How much longer will it take for the temperature of the teacup to decrease to 80 degrees Fahrenheit? That's our question. So first of all, we need a differential equation to represent something that changes based on a temperature differential. And so in this particular problem, we're going to let y be the temperature, and we're going to be looking at how the temperature changes with respect to time, and it's going to change in a way that's proportional to the difference between that temperature y and the temperature of the surroundings, in this case, the 60 degrees. Now we can solve this by separation of variables again. And I'll just remind you that is the second, really, and the more rigorous kind of differential equation solving that we do in this course. So we arrive here, and again, our familiar integrals, natural log of y minus 60 with all these growth and decay differential equations, kt plus c1, like this. And then we exponentiate, and we get y minus 60 is equal to e to the c1, e to the kt. Let's think about what temperature ranges we're looking at. We're thinking about something that's at a temperature that starts at 100 degrees. It's going to drop to 90, and it's going to drop to 80, and the temperature of the surroundings is 60. So really, we're only concerned with y being greater than 60 degrees here. And if y is greater than 60 degrees, we can say that y is equal to c, where c is equal to e to the c1, our constant, e to the kt. And then we have a plus 60 over here. So I did a couple things at once. I dropped the absolute value symbols because y was greater than 60 or equal to 60, we could say, because something doesn't drop below the temperature of its surroundings in terms of thermodynamics. So there's our basic equation, but we're missing two things. We have two unknowns. We don't know what the constant is, and we don't know what the decay constant is either. So we don't know C and we don't know K. However, we have information up above which will allow us to solve for these unknowns. And the first thing we're going to solve for is C. And to get C, well, let's start with y being equal to 100 degrees Fahrenheit. And the time when that is true is at 0 minutes. So we're going to put 100 in for y. And e to the kt becomes e to the k times 0. And then the plus 60. 100 is equal to, let's see, e to the k0 is e to the 0, which is 1. So that means 100 is equal to c plus 60, which means c is equal to 40. To get k, we're going to let y equal 90. That's degrees Fahrenheit. And we're going to let the time be 10 minutes, because 10 minutes goes by to go from 100 to 90. And we do that, we're going to have 90 is equal to 40 e to the kt plus 60. And as we solve, we'll get 30 is equal to 40 e to the kt. And we'll divide each side by 40. We'll get 3/4 is equal to e to the kt. And this ends up giving us k equals natural log of 3/4 divided by 10. And there are a few steps there that I skipped through. So there's our k value. And then we have our c value. And this means we can write y is equal to 40 e to the natural log of 3/4 over 10 times t plus 60. And there's our function for this teacup.